So today our guest speaker is Sushrut Dhangar. So he is doing masters in mathematics from IIT Guwahati, and today he will speak about residue theorems. Yep, over to you, Sushrut.
Yes, thank you, Arijit sir. Hello, everyone. I'll start my presentation. Um, as said, my topic for presentation is residue theorem. We'll be discussing the definitions of singular points and some important results leading to a residue theorem and some lemmas which will be used as tools in proving the Laurent series expansion and residue theorem. So let's start with what are regular points of a function. So if I have a function defined over a set open set omega to C with the points in omega where the function f is analytic are called as regular points. And what do we mean by singular points then? Singular point is actually a limit point of regular points of the function f. We have two different basic classification, two classification of singular points. One of them is isolated and the other is non-isolated. Well, we will be only dealing with the isolated singular points. So what are isolated singularities? So if f is said to have an isolated singularity at a point z equals a, if there exists r greater than 0 such that f is holomorphic in the punctured disk centered at a of radius r, but not on the entire disk. So we can imagine the function is actually defined in the punctured disk, but not at the point z equals a, and we will have the function is holomorphic on that punctured disk. So z equals a is hence called as an isolated singularity. And there are three types of isolated singularities. The first is a removable singularity, the other is poles, and the third is essential singularities. Let's quickly go through the definitions of all the three types. So the first is removable singularity. Like have the we have been introduced to the notion of removable discontinuity. In a similar fashion, we can define removable singularity, but with the help of holomorphic functions. Now, f has a we say f has a removable singularity at a point z equals a if we have some delta neighborhood of a over which we don't define, but we have a function g which is holomorphic over the disk b delta a, such that the function f and g agree with each other for every z in the punctured disk. All right, then we say that the function has a removable singularity. That is, so we do not define do not have a definition for the function f at z equals a, but we can always extend the definition of function f with the help of function g, so as to make the function holomorphic in the entire disk. Such is the idea behind removable singularities. Now let's talk about poles. So f is said to have a pole at z equals a if given any r positive, given any real number, positive real number, there exists a delta greater than 0 such that the modulus of fz is greater than r for any z in the punctured disk about z naught of radius delta. And lastly, we have the essential singularity that says that f has an essential singularity at z equals a if the limit as z goes to a of fz does not exist. Here does not exist in the sense that I can have two different limits, uh, two different values of this particular limit. So hence we say the limit does not exist. Now, there are some important theorems and results which actually are the building blocks for the um, Laurent expansion and residue theorem in turn. So one of them is the Cauchy integral formula, which all the master students must have uh, gone through. So formally, I'll just give the definition of, the theorem statement for Cauchy integral formula. So here we have an open set U, which is also a star-shaped set. So F is holomorphic in the, or F is holomorphic on U, and we consider gamma as a closed path in U. All right. Then given any A in U minus the range of gamma, this is nothing but the range of gamma. We have the 1 by 2 pi I integral over gamma of fw divided by w minus a dw is equal to f of a times 1 by 2 pi I integral over gamma of 1 by w by a w minus a dw. Now this is actually called as the winding number of gamma about point A. This is the winding number. So in a way, we are actually getting the value of the function at A with the help of this integral. Now let's move on with the Cauchy integral formula for derivatives. So the setup is same. F is a holomorphic function on U. U is open star-shaped set, and suppose we have a neighborhood of Z naught, B disk around Z naught of radius R completely inside U, and suppose we have a circular path, closed path of radius lying between 0 and R about Z naught inside this ball, right? So the nth derivative of F at any point Z inside this ball. So suppose this is our point Z naught and this is capital R. Now I'm taking a gamma path of radius small r, and inside this region, if I take any point Z, the derivative at that derivative, nth derivative of the function at that point is given uh, by the help of this expression, that is n factorial by 2 pi I integral over gamma r fw by w minus z whole raised to n plus 1 dw. Now we will be using these two theorems while proving the Lorentz expansion and residue theorem. Now let's see some equivalent statements on when can we say a point is removable singularity and vice versa. So the following statements are equivalent, saying that if z0 is a removable singularity of the function f, that is equivalent to saying that the limit as z goes to z0 of function f exists. Now the motivation behind this setup is, so by definition of removable singularity, we have a holomorphic function and a delta greater than 0 such that g is defined over this delta neighborhood of z0 to c, which is holomorphic, and they agree with each other for every point inside this punctured disk. Now if I take limit on both the sides, this is actually equal to limit as z goes to z0 of fz. Now since g is holomorphic, hence continuous as well, so this limit has to be some value gz0, actually the functional value of g at z0, and hence this value exists, and hence in turn we say that the limit is existing. Likewise we can go further that if the limit exists, limit f at z goes as z goes to z0 exists, this is equivalent to saying that f is locally bounded in the puncture disk, that is f is bounded in the disk centered at z0 but not exactly. So we are removing the point z naught, and which is actually, which is equivalent to saying that limit as z goes to z naught of fz times z minus z naught is equal to 0. Now let's see some equivalent statements for pole of a function. So z naught is said to be a pole of f if there exists m, uh, particularly pole of order m, if there exists m in naturals and a delta positive, and there exists a holomorphic function g defined on the delta neighborhood of z naught to c, such that fz is actually equal to gz by z minus z naught to the power m, right, for every z in the delta punctured disk about z naught, with g of z naught not equal to 0. So these conditions, so this equivalent statements are not hard to prove, one can easily prove them. And let's move on to the interesting and very important result, which is the Casorati-Weierstrass theorem. So this theorems, what it says is, if A is an essential singularity of function f in the open set U, then the range of this delta punctured disk, then the range of this punctured disk B dash AR, that is a disk of radius R centered at A, and we are removing the point A. This range is dense in C for every R positive, such that this disk is sitting inside Q. So this is some interest. These are some interesting results, and which are the building blocks of the theory of Lorentz series and residue theorem. Now let's talk about Lorentz series. Let's build some theory on Lorentz series. Now, if I have a series of the form summation n goes from negative infinity to infinity an, that is convergent. We say that is convergent if there exists a complex number s such that given any epsilon, there exists n such that this modulus, that is the partial sum a minus m to an minus s, is less than epsilon given any m and n greater than or equal to capital N. Now, an open question to the audience. So, is this statement? So, the statement says a minus n. So, we are taking this partial sum, which is like a negative n plus so on up to a n. This converges to s as n goes to infinity. Is this same as saying that the doubly infinite series, doubly infinite in the sense that n going from negative infinity to infinity an, this series will converge to s? So this is an open question. This is an open question to the audience. If anyone would like to volunteer for the same, can do so. Hello. Okay. Well, the answer to this question is pretty easy. I think one can actually sit and construct an example for the same. So I guess I will not be revealing the answer to this question. It is this. This question is from Kumresan sir's book, Complex Analysis on Complex Analysis. Now let's move on to the lemmas, which will be using as tools while proving the major theorems. So one of them is saying that if R positive is the radius of convergence of the power series, Fz defined as this series, power series. So summation n goes from 0 to infinity Cn z minus a to the power n. So if we have R as the radius of convergence, then the radius of convergence for this series, not radius of convergence, but particularly, but the values of z for which this series will be convergent, that is, the series is defined as summation n going from 0 to infinity of Cn times z minus a to the power negative n. So this looks like C naught plus C1 divided by z minus a plus C2 divided by z minus a to the power square, and so on. So this series is convergent when modulus of z minus a is greater than 1 minus r, 1 by r, which can be easily seen and proved, since this is so the radius of convergence is actually dependent on the coefficients, and we know that r is the ROC of this series. So In a way, we are saying that modulus of z minus a is less than r. Whenever this happens, the series is convergent, and we have just uh, we have just changed the index or the power of z minus a, and to have this series convergent, I just need that 1 over z minus modulus of z minus a is less than r, which is same as saying r is what we have is modulus of z minus a is greater than 1 by r. So this is pretty easy to imagine. Now, moving on to the important lemmas. So we'll name these lemmas as lemma 1 and lemma 2. So what lemma 1 says is that if I have a function which is holomorphic over the punctured disk centered at a of radius r, and if I take any r which is lying between 0 and capital R, with the help of this r, I am defining a closed circular path about centered at a of radius r. Then the function which takes r to integral over gamma r of f is constant. What it says is in particular that if I take two different radii lying between 0 and r, the integral over gamma r of f is actually equal to integral over gamma s of f. The proof of which is pretty uh, easy to understand. So the proof goes like this. So if I have, say, gamma r defined as the function, like if I define this as integral over gamma r of f, uh, and this is a one variable function, right? So where r is from the open interval 0 to r, right? Now if I have this, so then since this is a one variable function, if I get the derivative of this function is 0 throughout the region, throughout the values of r, then I can clearly say that the function itself is constant. So if I take the derivative of phi with respect to r, now by Leibniz's rule of differentiation, what we get is integral of gamma r of partial of f with respect to r, right? Now let's use the line integral formula. So here we have 0 to 2 pi of partial of f with respect to r of, here we have gamma. Let's substitute the value of gamma, that is a plus r e raised to it times, so the whole partial times r e raised to, so this is ri e raised to it and dt. So if we try to get the partial derivative of this, we end up with a derivative of f at a plus r e raised to it. We'll be applying chain rule here. So this gives us r e raised to it, and plus we have f of, what we get is a plus r e raised to it, and derivative of this with respect to r, which is I e raised to it. But here we left I e raised to it, which will be taking common. So here we have raised to it and dt, which can be also imagined as the partial derivative of f with respect to t. And since not just partial derivative of f, but f of a plus r e raised to it times r e raised to ri e raised to it. So this partial with respect to t, this is same as taking partial with respect to t and not r. Yeah. So this is actually equal to, so differentiation under the integral sign, we have the primitive. Hence, the value actually gives us 0. So we have the derivative value of phi with respect to r as 0. Hence, we can conclude that the function phi of r is constant. The function's value is constant throughout the open interval 0 to r. So Hence, if I change the radius, my integral over this gamma will not change, and we will be using this lemma. Now the lemma 2 is Cauchy integral formula for an annulus. An annular region is, if I have say a point z0 and I have two concentric circles of different radii, two concentric circles, like this is of radius say r1 and this is of r2. So this region is our annular region. Now, F be a holomorphic in this in a punctured disk about A of radius r, and if I take any z inside this punctured disk, and I can choose r1 and r2 in such a manner that z lies between the two annular region, two concentric circles. So this so z can lie between this two paths, gamma I circular paths. All right, and when doing so, given any z in this annular region, we can have fz define fz equal to 1 by 2 pi I times integral over gamma 2 of fw by w minus z dw minus 1 by 2 pi I integral over gamma 1 of fw by w minus z dw. Again, the proof of this is not so difficult. I'll give the a hint for how to prove this. So we just need to define a function fz as fw by fz, fw minus fz by w minus z. Here we are fixing z. Okay, we are fixing z. The variable here is w, and we are defining it piecewise. So since z, so w cannot be z here, and w's are coming from the puncture disk about AR, and W is equals to Z. When W is Z, we define the capital F W function as this. Now what happens is that we can we can claim that the function F is holomorphic in this puncture disk, and with the help of that and lemma 1 and lemma 1, I can actually show that if I take, say, so since we have chosen R1 and R2 uh, and have defined the circular paths about the point Z0, or so for here we have not Z0 but A. So here, if I take integral over gamma of 2, so we're defining R2 is greater than R1. So gamma 2 of f is actually equal to integral of gamma 1 of f. So 1 by 2 pi I, 1 by 2 pi I is because we are taking 2 pi because we have 2 pi i's here. And with the help of this, we can actually boil down to this result. All right. Now, let's move on with the, let's now build the Laurent expansion series for a holomorphic function on the annulus. Now, f is given okay, so assuming that f is holomorphic on the annulus region, then f is given by this infinite series that is going from negative infinity to infinity of an times z minus a to the power n times okay, so here an times z minus a to the power n, where z are coming from this annular region and ans are defined in such a manner. Now let's take gamma to be a path of so gamma to be a circular path about A of radius say P, which is lying between R and small r and capital R. So here is our annular region, right? Now the series converges absolutely and uniformly in the compact subsets of A. Now let's consider some compact subsets of A. All right. So let's consider some compact subsets. How do we consider compact subsets? So I take R1 and R2 such that R1 and R2 lie between small r and capital R. So such will be our construction, and R1 and R2 will correspond to the circular paths gamma R1 and gamma R2 centered at uh, point A. Right now, So this region, this annular region will be a compact subset. We'll also consider the we actually are considering the boundary. We are actually, you know, uh, concerned with the boundary points, that is the points lying on the uh, gamma of gamma I, whatever, gamma Ri. So Ri, right? Now what do we do here is, since from lemma 2 we know that the function fz is actually equal to what, 1 by 2 pi I integral, let's call this gamma 1 and this is gamma 2, gamma 1 of fw by w minus z dw minus 1 by 2 pi I. So this is gamma 2 integral over gamma 2 gamma 1 of fw by w minus z dw. What happens here is that now what I can do, I can actually uh, manipulate this 1 by w minus z term. How will I do that is, I take 1 by w minus z, I can rewrite it as w minus a minus of z minus a. And now, depending on the point gamma where it is coming from, so either it is coming from the range of gamma 1 or range of gamma 2, I can have two definitions of the this value. I mean, I can have two different values. I can define two different values for this expression. So if I take w, so let's actually see the picture. Here we have the point A. This is the radius r1. This is the radius r2. This is gamma 2 and gamma 1. Now if I have w on this gamma 2 path and z is lying between this, the modulus z z minus of a, so this distance, and if I take w here and this distance, the one with the greater modulus is modulus of w minus a, right? So if I have w inside gamma 2, what I can take is, I can take w minus a common. So I have w minus a, I take common and I rewrite this expression as 1 by, this is z minus a divided by w minus a, where w is coming from gamma 2. Now if w is coming from gamma 1, what I can do is, I can rewrite this expression as, I can take z, okay, I can, what can I do is, what I can do is, I can take z minus a common, and I can rewrite this expression as 1 minus w by minus a by z by z minus a. So this makes sense because w lies here. So here we have the w, and the, as you can see, the modulus of z minus a is actually greater than this. And why are we doing this? It's because we know that the geometric series converges to 1 by 1 minus z. I mean, this series z raised to n converges to this sum, this value, when mod z is less than 1. So that is our motivation here. So I can replace this expression by an infinite series here, and this expression with the help of this infinite series. And here we are not actually proving step by step the entire proof, but I'm just giving you the idea and sketch behind the proof of Lorentz expansion. So, so when we actually write this in the series form, what we get is, so fz can be written as, so here we get is, here what we get is, so this is what we have here is 1 by 2 pi I. So let's actually talk about the first part. So let's call this f2 and let's call this f1. So let's check what f2 gives us. So f2 is actually equal to 1 by 2 pi I of integral over gamma 2 of fw divided by w minus z dz. But we just now read try to manipulate this 1 by w minus z. Since w's are coming from gamma 2, so the description I'll be using is the first description, which says which can be replaced the 1 by 1 minus 1 divided by w minus z can be replaced with 1 divided by w minus a, right, times 1 minus z minus a divided by w minus a, right, which can be written as, so we know that 1 by 1 minus z minus a divided by w minus a is actually equal to the infinite sum n equals 0 to infinity of z minus a divided by w minus a whole raised to n. And we have the guarantee of this series being converging to this point because w's are from gamma 2, and I know that modulus of z minus a divided by w minus a is strictly less than 1. All right. With the help of this, I can now I can place it here. So this is 1 by 2 pi I integral over gamma 2 of fw divided by w minus a. Here what do we have? Z minus, so this is series n equals 0 to infinity of z minus a divided by w minus a to the power n. Now this is, so I can bring it inside. So this is gamma 2 of fw times summation n equals 0 to infinity of, I can actually bring f also inside. So this is n equals 0 to infinity of fw times z minus a to the power n divided by w minus a to the power n plus 1. Now, because gamma 2, so the points we are taking, right, gamma 2 and the points from where we are taking z, right, the region is compact, right, and because of that compact nature, I have uniform convergence of this series, and because of uniform convergence of the series, I can now interchange the integral sign and summation sign. So here we have 1 by 2 pi I of summation n going from 0 to infinity of integral gamma 2 of fw divided by w minus a to the power n plus 1 dw. I can rewrite this expression as in this form because now the integral is dependent on w and not z. So z minus a for this integral is kind of like constant. So I can pull out z minus a to the power n. Now, as we can see that this is looking in in a sense of a series, right? An infinite series n going from 0 to infinity of some coefficient times z minus a to the power n. And this is true for every z in the annular region inside the, we the points which the gammas which we chose. So this is true for every z in that annular region. And similarly for f1 function, I can get the series n equals negative infinity to negative 1 of integral over gamma 1 of fw divided by w minus a to the power, here we have, so I'll rewrite this in terms of positive uh, values. So this is k equals 0 to infinity of minus k dw whole times w minus a to the power minus k minus 1. Not w minus a, but z minus a. So again, here we have another series, right? So the major portion of our proof for the Lorentz expression is done. So with the help of f1 and f2, I can easily write fz as some series with positive powers of z minus a and some series with negative powers of z minus a. But here the gammas are different. This is gamma 2 and this is gamma 1. Here we are using the lemma 1, which we proved, that is, if I change the radius, the integral value does not alter. So I can take any row between r and small r and capital R, I can always get integral over gamma. So this gamma with respect to uh, rho, length rho, radius rho, is equal to integral over gamma 1, or say gamma 2. I'll call it gamma j. So I can replace both of these with summation integral. So n equals negative infinity to infinity of integral an times z minus a to the power n, where an's are defined in this fashion, which we are described in the statement. So that is 1 by 2 pi a integral over gamma fw by w minus a to the power n plus 1 dw, where gamma is this path, where p rho or p lies between r and small r and capital R. So such is the sketch. Basically, all the major steps we discussed here. So such is the sketch of a Lorentz expansion. And now let's move on to the main theorem, which I'm here to discuss. So before that, let's look at this definition we have here. So let gamma be a closed path in C, and let z naught be in C, be any point not in the range of gamma. So here z naught, okay, not in the range of gamma. Then the index of gamma with respect to z naught is this integral, which we discussed earlier in the session. And now, since now we have fz written as some series from negative infinity to infinity a n times z minus a to the power n. If I split the series into two parts, wherein the first part contains the powers of z minus a to be negative, and the other is z minus a powers are non-negative. The left portion is called as the principal part or singular part, and the other half is the analytic part. And we know that this power series is holomorphic function, right? So hence analytic part. And the other part, here we have 1 divided by z minus a to the power n. So such a form might not be analytic, right? So let's see what happens. Here the coefficient a minus minus 1. So a minus 1 is what? Integral over gamma, right? A minus 1 is this 1 by 2 pi I integral over gamma of fw divided by w minus a to the power n plus 1. N is minus 1. So this is no power of w minus a, and simply this integral fw dw. This is called the residue of the function f at a. So we denote residue of f at a in this fashion, and we have gamma to be a circular path of radius r centered at a, where small r is lying between 0 and r. And if f has a simple pole, now what do I mean by simple pole? Simple pole in the sense that the order is 1. The order of the pole is 1, uh, like we discussed in the definition above. So there the m would be 1. Now if suppose f has a simple pole at a, then clearly fz can be written in such a manner, right? Because the only coefficient of the negative terms would be c minus 1 divided by z minus a to the power n plus 0, and because the pole is of order 1, and the other half is the normal power series, uh, right, which is holomorphic. Right, so here we are writing G is the holomorphic part of the Lorentz expansion of f at A. Then we have the residue, we can get the residue of f at A with this formula, that is limit as z goes to A, z minus A times fz. Here we have a simple example on how we are using this formula to evaluate this residue of f at A, right? Now, coming to the residue theorem itself, what residue theorem says is that we have a star-shaped open set U, and we have finitely many points of distinct points in U where the function is not defined. The function is holomorphic in on u minus of these points, and we're letting gamma be any closed path in u such that, so gamma, so here in the diagram as you can see we have some singular points zi's, finitely many, and we have a gamma path, and the region opens at u. We have inside that we have these zi's and this gamma contour, right? Now integral over this gamma is actually equal to 2 pi I times summation of all the residues times the, what we have, uh, index or the winding number of gamma about zj, each zj. All right. So let's move on to the proof of residue theorem. Uh, the idea is we actually try to get a delta positive. We try to get a delta positive. Actually, we can choose a delta positive because U is an open set, such that this delta is equal to half times minimum of minimum of distance between Zj and the range of gamma, comma, distance between the two residues itself, Zi and Zk, such that where j lies between 1 and m, so we have m residue, m points of m singular points, so this j goes from 1 to m, and I not equal to k lying between 1 and m. So we take such a delta, and if we take such a delta, we can see that any ball of this delta radius about zj will not intersect the range of gamma, so the intersection would be empty. And lastly, we will also have that the balls about zj and distinct points zk.
Sushrut,
Yes, sir.
sorry for interrupting. How much more time do you need?
Only 5 minutes, sir. We'll conclude this theorem in 5 minutes.
Yeah. Okay. Wind up.
Yeah. So this intersection will also be empty. And now, with the help of this idea, let's now quickly go through the proof of this. So this is all the construction we need. And now we'll define fj as the um, singular part of the function f defined about zj. Okay, so that would be n equals 1 to infinity of c of minus n j. Let's have this index z minus zj to the power minus n. Now this is a singular part of f at zj. Now the infinite series is uniformly convergent on the compact subsets of c minus of their closed wall b zj delta. Okay, as we discussed in the Lorentz series expansion, uh, the series will be uniformly convergent over the compact subsets, right? So that is what we are doing here. So basically, for in particular, so this series would be convergent in the compact subsets of C minus of B Zj delta. And then in particular, see gamma is not inside, is not intersecting with any Zj. So in particular, gamma is a compact subset, right, of this region. So this series will be uniformly convergent on gamma as well, or the points of gamma as well. So the function fj is fj function is also this is like some power series, and fj will be holomorphic on all the other zk's where k is not equal to j as well, right? And then what I can have is the function f minus fj is holomorphic on zj. And why is that? This is because we are removing the singular part of function f, and we are only remained with the analytic part, and that is the by saying analytic. it is actually an holomorphic or at Zj as well then, right? So F minus Zj is holomorphic on Zj at Zj, and Fj is holomorphic at Zk for any k not equal to 0. So in particularly, I can have the sum k equal to 1 to m where k is not equal to j. F of k is holomorphic on Zj, right? And with the help of this, I have the, if I define g as f minus summation of, we have k equals 1 to m of fk. This is holomorphic at Zj for each j. Try to think over this once. And hence, we say that G is holomorphic on U. Now, what does that help us, give us? U is star shape. G is a holomorphic function. G is defined in such a fashion. Then, what do we have here? The only thing remaining is to apply Cauchy's theorem. Applying Cauchy's theorem over gamma, this is 0, which gives us, if we rearrange the terms, we get integral over gamma of f is equal to integral over gamma of summation k equals 1 to m of fk. Sorry, this would be summation k equal to, yeah, I mean, I can have this integral, and then since we have finite integrals, I can take the summation outside. So this is k equal to 1 to m of fk. Now, what we do is we write the expansion of fk, which is nothing but summation n going from 1 to infinity of c of minus n j, not j, here k index, and z minus z k to the power, so this to the power of minus n. Now what we can do is, again, because of compactness of gamma, I can, the points we are having here are just the points of gamma. So because of uniform convergence, because of compactness, we have uniform convergence of the series, and hence we can take summation outside. So we have k equals 1 to m summation n equals 1 to infinity of integral over gamma of c of minus n k z minus zk to the power minus n. And this is constant, so I can write it here, right? Now let's look at this integral. So this is integral 1 by z minus zk to the power n. Now this integral is somewhat familiar to us, right? This is nothing but, this actually is equal to, this boils down, since we have an infinite sum n going from 1 to infinity. If I have n greater than 1, this integral will always give us value 0 because of the existence of primitive of 1 by z minus zk to the power n, where n is greater than 1. Because of the existence of primitive, the integral over this closed path will be 0, and hence what we are left with is summation k equals 1 to m of only the n equals 1 part, and that is integral over gamma of 1 by z minus zk dz. This is nothing but the winding number, and this we defined as the residue of f. So this is particularly equal to c of, so this is k equals 1 to m of residue of f defined at zk times 2 pi I. Right here we have 2 pi I, 1 by 2 pi I missing. So this integral is actually 2 pi I. This integral is actually equal to 2 pi I times the winding number of gamma about zk. And so we just substitute the values here, and hence we have now got the form which we were aiming to get. So this is the residue of f with respect to the singular point zk times gamma zk. So this is the proof of residue theorem. And before concluding the session, I have a question which Pradeep sir when I was discussing this theorem with Pradeep sir, he asked me this question, that why are we dealing with only finitely many isolated singularities here? Why can't we have infinitely many isolated singularities? This is an open question to the audience. If anyone would like to think an answer to this question, please do so. And I can always rephrase the statement of residue theorem in the form of, suppose f is analytic in the region u except for some finitely many isolated singular points zi I going from 1 to m, and gamma is closed path which does not pass through any zi, then the this is the statement we have. So does anyone have any clue on how we will deal with if we have infinitely many isolated singularities? Okay, so if not, so I'll quickly give the description why infinitely many will actually boil down to the finitely many isolated singularities. Is because if so this contour gamma, the region inside it is including the boundary. This is compact subset of C. And if I have infinitely many points, see, if I have Zj outside, I do not bother because the index of gamma about Zj will be 0. So that will not even contribute, that will not contribute anything. If I have infinitely many points inside this compact subset, singular points inside this isolated singular points inside this compact subset, now what happens is, because it is compact, then uh, I'll have a subsequence which is converging, right? So I'll have subsequence of uh, singular isolated singular points converging to a point, but that actually what it does is it contradicts the nature of isolated singularities, right? Because given any neighborhood of gamma, sorry, neighborhood of gamma, function is holomorphic, but always get a point, because the sequence is convergent. I'll always get a point where the at the point of convergence, I'll always get a point that also will be a non isolated singularity, right? And here that if I take any neighborhood, I'll always get another point as well where the function is not holomorphic, which cannot be true since the function itself is isolated. So hence we can only have finitely many single isolated singularities inside this contour, inside the contour region. So with that, I conclude my session. Thank you for listening.
Thank you, Sushrut. If there is any question from the audience, then you can ask. Okay. So thank you very much, Sushrut, for your wonderful talk.